This is a demonstration of Liqid Slurm integration using a simple 2-node Slurm cluster. In this demo, I will submit a job to our Slurm controller requesting a single GPU for processing. But before I do that, there are a few things I would like to draw your attention to. First, this fabric is composed of 2 CPUs, 2 GPUs, and 4 SSDs. When our example job is submitted to the Slurm controller, we will see a single GPU move out of the fabric's free pool into our Slurm group, and then finally into one of the 2 available Slurm nodes. At the same time, Slurm will select a pseudonode that best meets the hardware requirements of the given job. Now, it's important to note that pseudonodes are a representation of potential hardware combinations that can be configured within the fabric. When Slurm selects a pseudonode for a given job, Liqid Slurm integration will identify the requested hardware resources and provision it within the fabric. Additionally, Liqid Slurm integration will then disable any no longer valid hardware combinations. In the context of Liqid Slurm integration, pseudonodes can exist in one of 4 states: cold, warm, active, and disabled. A cold pseudonode is one that is available to Slurm for provisioning. An active pseudonode is one that has been provisioned and is currently processing a job. A warm pseudonode is a node that has been provisioned but is not currently processing any jobs. And a disabled pseudonode is a node that is no longer available to Slurm for provisioning. Now, with all that in mind, let's submit a job to our Slurm controller and watch what happens. As you can see, this single GPU job has moved a GPU from our free pool and into Fabric Node 1. Now that our job is finished processing, the active pseudonode has been moved to a warm pseudonode state. A warm state is now waiting for additional jobs that meet those hardware requirements in order to reduce the startup time of provisioning new nodes. Additionally, we can see that all pseudonode combinations that are no longer viable are still marked as disabled, and every other still viable hardware combination is marked as cold. To demonstrate how Slurm reuses warm pseudonodes to reduce the startup time of consistent job requirements, let's re-queue our original job and watch how our warm pseudonode disappears from our list into an active state and then moves back into the warm state. Now you may be wondering why it disappeared from a warm state instead of moving into an active state. This is due to the implementation of my helper tool here, which simply doesn't refresh enough to catch it moving into an active state and then back into a warm state. Now, the timeout in our lab is about 9 minutes, which means that when this warm pseudonode has sat idle for about 9 minutes, Slurm will automatically deprovision it and return it and all of the disabled pseudonodes back into the free pool. Now that our pseudonode has sat idle for about 9 or so minutes, you can see that it has now moved back into a cold state. And over on the left-hand side, you will see the fabric start to deprovision itself and return that single GPU back into the free pool.